Welcome to Spring LIB.
This is chapter 37, problem number 62. In part A, there's a space ship that is approaching towards us, and it's emitting EM waves. And we are asked to calculate in part A. We are asked to calculate relate the periods of what we're receiving on Earth to the period that is emitted by the ship itself. So in this case, actually, T, 1 over F, let's say, emitted by the ship is going to be our proper time. So T is here, the proper time. So if you remember the formula for the time dilation, we have proper time on the left equals to the time divided by gamma, right? But now our proper time is T. T equals T naught over gamma is what we're going to have. And from the periods, let's go towards the frequencies because that's what's asked. So as you know, the frequency is the inverse of the period. And in this case, if we write the left-hand side of this equation, 1 over F, then T naught will be 1 over F naught, and we have a gamma factor here. From here, F is going to be equal to F naught gamma. Now, this is the general formula, right? Gamma being, let's remember what gamma was, 1 minus V squared over C squared. If you can plug it in this equation, then the frequency is going to be F naught, the frequency 1 over, 1 over square root of that term that we put there, 1 over square root of 1 minus V squared over C squared, right? So we know that the gamma factor is always greater than 1. Going back to this equation, if gamma factor is always greater than 1, that means our F is always going to be greater than F naught. That's also something that is asked in the problem part A. Now, moving on to part B. In part B, if F naught is 345 megahertz and the speed now is 0.758 c towards us, it's approaching, the ship is approaching towards us, but it's going to pass by us and it's going to be moving away, right? So we're asking what is F when the ship is approaching us in the first part of part B. So as you know, we're going to use the relative Doppler equation. F is going to be equal to F naught. For when it's approaching us, it's going to be C plus V over C minus V. Everything is pretty much given in this problem. 345 megahertz. I'm not going to convert it to hertz because this term here, 1 over, the square root term is just a number. It's just a ratio. So I don't want to convert back and forth. Now, square root of C plus V is 0.758 C over C minus 0.758 C. If you do algebra here, what you're going to get is 929.87 megahertz. When the ship is moving away, then we have F equals F naught, C minus V over C plus V. Then if we do the same, 345 megahertz, square root of C minus 0.758 C divided by C plus 0.758 C, then we get 128 megahertz from there. Now in the other part of the same, we're still solving part B. There are several questions listed in part B. So in either case, we want to calculate the shift of F minus F naught. Again, F naught is 345. So 929.87 minus 345 is how we calculate the shift. For the first case, it's 584.87 megahertz. And then for this case, F minus F naught is going to be something negative, actually, 128 minus 345. That is negative 217 megahertz, right? Now in part C, what we are asked is, well, we want to use the result in part A. Use result in part A to calculate F and the shift, okay? And then, well, let's do it first. So the equation that we derived in part A was F naught times gamma equals F, correct? And we said that this equals to F times 1 over square root of 1 minus V squared over C squared. So now if we assume that still F naught is 345 megahertz using the first approach that we generated in part A, then we're going to have 0.758 C squared. What we have is 528.93 megahertz. Now let's look at the shift then. The shift is going to be 528.93 megahertz minus 345 megahertz, which happens to be 183.93 megahertz. This is the shift. We got this shift and the frequency using the formula that we derived in part A. And now we're going to compare this method to the method that we used in part B. Remember the Doppler equation? So the question is again, how does it compare to part B? What do we get in part B? For when the ship is moving towards us, the shift was found to be 584.87 megahertz, if you remember. When it's moving away, after it's passed by us, it's moving away from us, the frequency shift was negative 217 megahertz. Now, let's look at these two and figure out how it compares to this number. If you just quickly look at it, and if you take the average of these two, moving towards us and moving away from us, when you take the average, what you get, let's see, is 584 plus 87 plus, which is minus 217, right? Divided by half. What do you think this is equal to? Equals to 183.93 megahertz. So we're basically finding the average frequency by using the formula that we derived in A. But if you want to be specific as the ship is approaching us, what the frequency shift would be, and as it's going away from us, what the frequency shift would be, then we would use the regular Doppler relativistic equation.